Welcome! In this session, we'll tackle the problem LeetCode number 772, Basic Calculator 3. This is a challenging yet fascinating problem that involves parsing and evaluating mathematical expressions, including operators and parentheses. Get ready to explore efficient approaches to solve this step by step. In this problem, we are tasked with evaluating a mathematical expression provided as a string. The string can include integers, the basic arithmetic operators plus, dash, asterisk, and forward slash, as well as parentheses, which are used to change the order of operations. One important detail to note is that division should truncate the result towards 0. For example, if the division yields a result like 2.9, it would truncate to 2. The string is guaranteed to represent a valid mathematical expression, and all intermediate results will fit within the range of a 32-bit signed integer. The input will be a string of length between 1 and 10,000 characters, and our goal is to return a single integer value representing the result of evaluating the expression. Consider the first example. If the input string is 1 plus 1, the output is simply 2. This is because the expression involves basic addition, 1 plus 1 equals 2. Now, for a slightly more complex example, let's look at the input string 6 to 4/2. Here, we must follow the operator precedence rules. Division takes priority over subtraction, so we first compute 4 divided by 2, which equals 2. Then, we subtract this result from 6, giving us the final answer of 4. Now, let's analyze a more intricate example. For the input string 2 times open parenthesis 5 plus 5 times 2 close parenthesis divided by 3 plus open parenthesis 6 divided by 2 plus 8 close parenthesis, we start by evaluating the expressions inside the parentheses. First, within the inner parentheses, we compute 5 plus 5 times 2. Since multiplication has higher precedence than addition, we calculate 5 times 2, which is 10, and then add 5 to get 15. For the outer parentheses, we calculate 6 divided by 2, which equals 3, and add 8 to get 11. Substituting these results into the main expression, it becomes 2 by 15/3 plus 11. Next, we handle multiplication and division from left to right. 2 times 15 equals 30, and 30 divided by 3 gives 10. Finally, adding 10 and 11 gives the result 21. For an even more complex case, let's review the input open parenthesis 2 plus 6 times 3 plus 5 minus open parenthesis 3 times 14 divided by 7 plus 2 close parenthesis times 5 close parenthesis plus 3. We begin by evaluating the innermost parentheses. Here, 3 times 14 divided by 7 equals 6, as division takes precedence. Adding 2 to this result gives 8. Substituting back, the expression becomes open parenthesis 2 plus 6 times 3 plus 5 minus 8 times 5 close parenthesis plus 3. Next, we process multiplication and division in order. 6 times 3 equals 18, and 8 times 5 equals 40. Simplifying further, we have open parenthesis 2 plus 18 plus 5 minus 40 close parenthesis plus 3. Now, we handle addition and subtraction from left to right. 2 plus 18 gives 20, plus 5 equals 25, minus 40 equals minus 15, and finally, adding 3 results in minus 12. Finally, let's review the constraints of the problem. The length of the input string will be at least 1 and at most 10,000 characters. The string will only consist of digits, the operators plus, dash, asterisk, forward slash, and parentheses. All integer values and intermediate results during evaluation are guaranteed to stay within the range of a 32-bit signed integer, which means between -2 raised to the power of 31 and 2 raised to the power of 31 minus 1. Additionally, the division operator always truncates towards 0. Importantly, the problem guarantees that the input expression is valid, so we don't need to handle any invalid cases. This ensures our focus remains solely on implementing the logic to evaluate the expression correctly. To solve LeetCode number 772, which involves evaluating a mathematical expression string containing integers, operators like addition, subtraction, multiplication, division, and parentheses, we need a strategy that accounts for both operator precedence and the presence of nested expressions. One approach to consider is the brute force method using recursion. The intuition behind this method is to systematically break down the problem into smaller subproblems by handling parentheses and operator precedence through recursive calls. As we traverse the input string, we build numbers from consecutive digits, and when we encounter operators or parentheses, we delegate the evaluation of sub-expressions to recursive calls. A stack is used to manage numbers and operators, ensuring that operations are applied in the correct order. This approach is conceptually simple, as recursion naturally mirrors the structure of nested parentheses and operator precedence, but it comes with certain limitations that we will explore next. The recursive brute force approach has a time complexity of O(n squared, in the worst case, primarily due to the repeated slicing of the string during recursive calls. For example, every time we encounter a parenthesis, we create a new sub-expression, which adds overhead to the process. Additionally, the space complexity is O(n), as the recursive call stack grows with the depth of nested parentheses, and we also use a separate stack to manage operators and numbers. While this approach is straightforward, its inefficiency becomes evident when dealing with larger strings or deeply nested expressions. This necessitates a look into more optimized methods, such as iterative parsing, which avoids the overhead of recursion while still handling operator precedence and parentheses effectively. The iterative parsing approach builds on the limitations of recursion by using two stacks, one for numbers and another for operators, to simulate the evaluation process iteratively. This gives us more control over the flow of the computation and eliminates the need for recursive calls. As we traverse the string, we push numbers onto the number stack and operators onto the operator stack. Parentheses are handled by temporarily suspending the current evaluation until the closing parenthesis is encountered, at which point we resolve the sub-expression within the parentheses. Operator precedence is managed by evaluating the top of the stacks whenever an operator of lower precedence is about to be pushed. This ensures that operations are carried out in the correct order. With a time complexity of O(n), where n is the length of the input string, and a space complexity of O(n) for the stacks, this method is efficient and well-suited for handling complex expressions. While the iterative parsing approach is efficient, it does have some drawbacks. The implementation is more complex than the recursive method, as it requires meticulous handling of operator precedence and parentheses using stacks. This added complexity can make the code more challenging to write and debug, especially for beginners. An alternative approach worth considering is the shunting yard algorithm, which converts the infix expression into reverse Polish notation, or RPN, before evaluating it. The intuition here is to first transform the expression into a format that eliminates the need for parentheses and directly encodes operator precedence. This involves using a stack-based algorithm for the conversion, followed by a single stack to evaluate the RPN. While elegant and efficient with a time complexity of O(n), the need for an additional conversion step makes it less direct than the iterative parsing approach. Among the various strategies discussed, the iterative parsing approach using stacks emerges as the preferred solution for this problem. It achieves an optimal balance between efficiency and clarity, avoiding the inefficiencies of recursion while directly handling operator precedence and parentheses. A key realization that makes this approach so powerful is the use of separate stacks for numbers and operators. This separation allows us to systematically evaluate expressions in the correct order, even in cases involving nested parentheses or complex precedence rules. When compared to the other approaches, the recursive method is simpler but suffers from inefficiency, and the shunting yard algorithm, while elegant, introduces unnecessary complexity with its additional conversion step. The iterative parsing approach, on the other hand, is both efficient and intuitive, making it the ideal choice for solving this problem. The iterative stack-based approach is chosen primarily for its efficiency and simplicity in managing operator precedence and parentheses without relying on recursion. With a linear time complexity of O(n) and a clear, systematic method for evaluating expressions, it strikes the perfect balance between performance and clarity. This approach is particularly suited for solving LeetCode number 772 because it handles the most challenging aspects of the problem, nested parentheses and operator precedence, seamlessly. Ultimately, its combination of practicality and elegance makes it the most robust and scalable solution among the alternatives considered. To solve this problem, we need to evaluate a mathematical expression provided as a string. The string can include integers, the operators for addition, subtraction, multiplication, division, and also parentheses. Since operator precedence and parentheses significantly affect how the expression is evaluated, our solution must handle these aspects correctly. The first step is pre-processing the input, which involves removing spaces to make parsing straightforward. Additionally, helper functions are defined to handle specific tasks like parsing numbers, operators, and parentheses. The core idea of the algorithm revolves around using two stacks. The operand stack is used to store numbers, while the operator stack keeps track of operators and parentheses. These stacks help manage operator precedence and ensure that parentheses are processed correctly, which is the primary challenge in this problem. Now, to evaluate the expression, we iterate through each character in the string. If the character is a digit, we parse the entire number, such as 123, and push it onto the operand stack. For operators like plus, dash, asterisk, or forward slash, we need to consider precedence. If there's an operator on top of the operator stack with greater or equal precedence, we process it by popping from both stacks, computing the result, and pushing the result back onto the operand stack. Only after resolving higher precedence operations do we push the current operator onto the stack. Parentheses require special handling. When encountering an opening parenthesis, we push it onto the operator stack. For a closing parenthesis, we process all operators until we find the matching opening parenthesis, which is then removed from the stack. Finally, after iterating through the string, any remaining operators on the operator stack are processed, and the top of the operand stack will hold the result of the expression. There are some key insights that make this algorithm efficient. First, operator precedence is crucial. Multiplication and division have higher precedence than addition and subtraction, and this is managed dynamically using the operator stack. Parentheses, on the other hand, override normal precedence. When a closing parenthesis is encountered, operators are processed until the corresponding opening parenthesis is found. This ensures that operations within parentheses are handled first. The algorithm is efficient because it processes one character at a time and resolves higher precedence operations immediately, avoiding the need for complex recursion. The two-stack approach plays a pivotal role here. The operand stack stores numbers, either as they are parsed or as intermediate results of computations. The operator stack temporarily holds operators and parentheses, ensuring that precedence and parentheses are handled correctly. The algorithm is highly efficient, with a time complexity of O(n), where n is the length of the input string. Each character is processed only once, and stack operations like push and pop are constant time. The space complexity is also O(n), as the stacks may grow to store all numbers and operators in the worst-case scenario, such as deeply nested expressions. Let's see an example with the input s equals 2 asterisk 3 plus 5 slash 4 dash 6. Parsing begins with the number 2, which is pushed onto the operand stack. The asterisk operator is then pushed onto the operator's stack, followed by the opening parenthesis. Inside the parentheses, 3 and 5 are parsed and pushed onto the operand stack. The plus operator is processed next, resulting in 3 plus 5 equals 8, which updates the operand stack. The opening parenthesis is then removed. The asterisk operator is processed, giving 2 asterisk 8 equals 16, and the operand stack is updated again. Next, the division operator forward slash is pushed, and the number 4 is parsed. Processing forward slash results in 16 slash 4 equals 4, updating the operand stack once more. Finally, the subtraction operator dash is pushed onto the operator stack, and the number 6 is parsed and pushed onto the operand stack. The last step is to process the subtraction operator, which results in 4, 6 equals dash 2. At this point, the operand stack contains the final result, dash 2, which is returned. To optimize further, we can avoid string conversions by using an index pointer to process numbers directly, making parsing faster. Additionally, the algorithm can be extended to handle a unary minus, such as dash 3. Edge cases must also be accounted for. For example, an empty string should return 0, and a single number should simply return that number. Nested parentheses must be handled correctly to ensure proper precedence, and division by 0 should trigger an appropriate error or return a defined value. Lastly, malformed inputs must be validated to prevent unexpected behavior during parsing. Here, we start by defining a class called solution and implementing a method named calculate that takes a string s as input. Within this method, there's a helper function called evaluate which is used to process the tokens of the expression and compute the result. Inside evaluate, we initialize an empty stack, a variable number to track the current number, and a sign variable to store the current operation, which starts with plus. The function iterates through the tokens, and if a token is a digit, it updates number with its integer value. If the token is an opening parenthesis, we call evaluate recursively to handle the sub-expression within the parentheses. When we encounter an operator or reach the end of the tokens, we process the current number based on the last operation stored in sign. For example, if the sign is plus, we push number onto the stack, or if it's dash, we push the negative of number. For multiplication and division, we perform the operation with the top value on the stack and update it accordingly. Finally, we update the sign to the current token, preparing for the next operation. Next, we reset number to 0 after processing the current token. If a closing parenthesis is encountered, we exit the recursion by breaking out of the loop and returning the sum of the stack, which represents the result of the sub-expression. Outside the evaluate function, we tokenize the input string s. This is done by iterating through each character and grouping multi-digit numbers together. If a character is not a space, it is added to the tokens list, while spaces are simply ignored. Once the tokenization is complete, we pass the tokens list to the evaluate function to compute and return the final result. This implementation handles nested parentheses, operator precedence, and multi-digit numbers, ensuring the expression is evaluated correctly. Here, we begin by defining a Java class called solution that implements a method named calculate. This method takes a string s as input, which represents the mathematical expression to evaluate. The first step is to tokenize the input string. To do this, we call a helper method named tokenize, which processes the string and breaks it into a list of individual tokens. These tokens include numbers, operators like plus, dash, asterisk, and forward slash, as well as parentheses. Inside the tokenize method, we use a while loop to iterate through the characters of the string. If a character is a digit, we build the complete number using a string builder, ensuring multi-digit numbers are handled properly. Non-digit characters, like operators and parentheses, are added directly to the token list. Spaces are ignored entirely. Once tokenization is complete, we return the list of tokens for further processing. The next stage involves evaluating the list of tokens using the evaluate method. Here, we use a stack data structure to manage intermediate results, which is critical for handling operator precedence and parentheses. We initialize a variable number to hold the current number being processed and a variable sign to track the current operation, starting with plus. As we process each token, we check whether it's a number or a special character. If the token is a number, we parse it into an integer and store it in number. If the token is an opening parenthesis, we recursively call the evaluate method to handle the expression inside the parentheses. When we encounter an operator or reach the end of the tokens, the current operation is applied based on the sign variable. For example, if the sign is plus, we push the current number onto the stack. For dash operations, we push the negative of the number. Multiplication and division are handled by popping the last number from the stack, applying the operation, and pushing the result back onto the stack. The evaluation process continues with division, where we divide the top of the stack by the current number and push the result back onto the stack. After processing the current token, we update the sign variable to the current operator and reset number to 0. If a closing parenthesis is encountered, we exit the current recursive evaluation by breaking out of the loop. Once all tokens have been processed, we calculate the final result by summing up all the values in the stack. Since the stack contains the results of operations in the correct order, the sum gives us the final evaluated value of the expression. Lastly, the isNumber helper method checks if a token is a valid number by ensuring all its characters are digits. This completes the implementation, providing a robust solution for evaluating mathematical expressions with support for integers, operators, and nested parentheses. To solve the expression 2 times open parenthesis 3 plus 4 close parenthesis, we start by breaking it into tokens through a process called tokenization. This involves scanning the string and separating numbers, operators, and parentheses into individual components. For this input, the tokens are 2, asterisk, 3, plus, 4, and. Next, we begin evaluating these tokens using the evaluate function. Initially, the first token is 2, which is a number, so we update our number variable to 2 and move to the next token, leaving the tokens as asterisk 3 plus 4 and. The next token is asterisk, which is an operator. Since this marks the end of processing the previous number, we push the value of number, which is 2, onto our stack. The stack now contains 2. We then update the current operator, or sign, to asterisk, reset number to 0, and continue. The next token is, which is an open parenthesis. This indicates a sub-expression, so we call the evaluate function recursively to handle the tokens inside the parentheses, 3, plus, 4, and. Inside this sub-expression, the first token is 3, a number, so we update number to 3 and move the tokens forward to plus, 4, and. In the sub-expression, the next token is plus, an operator. We push the current value of number, which is 3, onto the stack. The stack for the sub-expression is now 3. The sign is updated to plus, number is reset to 0, and the tokens advance to 4 and. The next token is 4, another number, so we update number to 4 and move the tokens forward to. Finally, when we encounter the closing parenthesis, we push the current value of number, which is 4, onto the stack. The sub-expression stack now contains 3, 4. To compute the result of the sub-expression, we sum the values in the stack, yielding 3 plus 4 is equal to 7. We return this result, 7, to the main evaluation, and number is updated to 7. Back in the main evaluation, we continue by performing the multiplication indicated by the operator asterisk. We pop the top value from the stack, which is 2, and multiply it by the current value of number, which is 7. This gives us 2 times 7 is equal to 14. We push this result, 14, back onto the stack, so the stack now contains 14. At this point, we have no more tokens left to process. The final result of this expression is the sum of the stack, which is 14. Moving on to another example, we consider the expression open parenthesis 2 plus 3 close parenthesis times 5. After tokenizing, the tokens are 2 plus 3 comma asterisk and 5. We begin evaluating these tokens, starting with the first token, which is. This indicates a sub-expression, so we recursively evaluate the tokens inside the parentheses, 2, plus, 3, and. Within the sub-expression 2 plus 3, the first token is 2, a number. We update number to 2 and advance the tokens to plus, 3, and. The next token is plus, an operator. We push the current value of number, which is 2, onto the stack. The sub-expression stack now contains 2. We then update the sign to plus, reset number to 0, and proceed to the next token, which is 3. Since 3 is a number, we update number to 3 and advance the tokens to. When we encounter the closing parenthesis, we push the current value of number, which is 3, onto the stack. The stack for the sub-expression now contains 2, 3. To compute the result of the sub-expression, we sum the values in the stack, giving us 2 plus 3 is equal to 5. This result, 5, is returned to the main evaluation, and number is updated to 5. Returning to the main evaluation, the next token is asterisk, an operator. We push the current value of number, which is 5, onto the stack. The stack now contains 5. We update the sign to asterisk, reset number to 0, and move on to the next token, which is 5. The final token in this example is 5, a number. We update number to 5. Since the current operator is asterisk, we pop the top value from the stack, which is 5, and multiply it by the current value of number, which is also 5. This gives us 5 times 5 is equal to 25. We push this result, 25, back onto the stack, so the stack now contains 25. At this point, there are no more tokens left to process. The final result of the expression open parenthesis 2 plus 3 close parenthesis times 5 is the sum of the stack, which is 25. Now, let's analyze a third example, 3 plus 5 slash 2. After tokenizing, the tokens are 3, plus, 5, forward slash, and 2. We begin evaluating the tokens, starting with the first token, 3. For the expression 3 plus 5 slash 2, the first token is 3, which is a number. We update number to 3 and advance the tokens to plus, 5, forward slash, and 2. The next token is plus, an operator. We push the current value of number, which is 3, onto the stack. The stack now contains 3. We then update the sign to plus, reset number to 0, and proceed to the next token, which is 5. Since 5 is a number, we update number to 5 and advance the tokens to / and 2. The next token is / an operator. We push the current value of number, which is 5, onto the stack. The stack now contains 3, 5. We update the sign to /, reset number to 0, and move on to the next token, which is 2. The final token in this example is 2, a number. We update number to 2. Since the current operator is /, we pop the top value from the stack, which is 5, and divide it by the current value of number, which is 2. This results in 5 divided by 2 is equal to 2, integer division. We push this result, 2, back onto the stack. The stack now contains 3, 2. At this point, there are no more tokens left to process. The final result of the expression 3 plus 5/2 is the sum of the stack, which is 3 plus 2 is equal to 5. To analyze the time complexity of our solution, we start by breaking it into two main parts, tokenization and recursive evaluation. First, during tokenization, the algorithm scans through the input string character by character. For example, when it encounters a multi-digit number like 123, it continues iterating to capture the entire number as a single token. This ensures that every character in the input is processed exactly once. As a result, the time complexity of the tokenization step is O(n), where n represents the total length of the input string. Now, let's examine the evaluation phase, where the algorithm processes the tokens recursively. At each level of recursion, the function iterates through the tokens to perform operations such as addition, subtraction, multiplication, or division. If parentheses are found, the function evaluates the expression inside them by making a recursive call. The recursion depth, denoted as d, depends on the maximum nesting of parentheses. At each level of recursion, all tokens within that scope are processed, which can take O(n) time in the worst case. Combining this, the overall time complexity of the evaluation phase is O(n*d). In the best case, with no parentheses, the recursion depth is 1, and the complexity is O(n). For moderate nesting, where d is small compared to n, the average case complexity is also O(n). However, in the worst case of deeply nested parentheses, d can become proportional to n, leading to a worst-case complexity of O(n²). Moving on to space complexity, the solution has three contributing factors. First, the token storage. The parsed tokens are stored in a list, and in the worst case, each character in the input string becomes a token, resulting in O(n) space. Second, the evaluation stack. While processing the tokens, the stack temporarily holds numbers and intermediate results for the current scope, which also requires O(n) space in the worst case. Finally, there's the recursion stack, whose depth depends on the maximum nesting of parentheses, or d. This contributes an additional O(d) space complexity. Combining these, the overall space complexity is O(n plus d). In the worst case, where the depth d equals the length of the input n, the space complexity becomes O(n). Let's compare this approach to others. A brute force or naive method might involve directly iterating through the string and evaluating expressions without tokenizing or handling operator precedence correctly. This would likely require multiple passes over the string, making it inefficient. Our solution improves upon this by using a recursive approach that processes the expression in a single pass per recursion level, handling operator precedence and parentheses effectively. Compared to more optimized methods, such as iterative algorithms that use explicit stacks like the shunting yard algorithm, our recursive solution is clean and concise, achieving O(n) time complexity for most practical cases. To summarize, the time complexity is O(n) in the best and average cases, and O(n² in the worst case due to deep nesting. The space complexity is O(n), accounting for tokens, the evaluation stack, and the recursion stack. This makes the solution efficient for typical inputs, though performance can degrade with excessive nesting due to its recursive nature. When solving basic calculator 3, there are a few common pitfalls to watch out for. One major mistake is ignoring operator precedence. For instance, in the expression 3 plus 2 by 2, multiplication has a higher precedence than addition, so the correct result is 7, not 10. To address this, you can use a stack or recursion to manage precedence explicitly. Another frequent issue is mishandling parentheses. Parentheses create new precedence rules, and failing to evaluate them properly can lead to incorrect results. For example, open parenthesis 1 plus 2 close parenthesis times 3 should evaluate to 9, not 7. Using recursion or a helper stack to isolate and evaluate sub-expressions within parentheses can resolve this. Additionally, integer division errors are a common source of bugs. In Python, the division operator / produces a float result, which might not align with the problem's constraints. Instead, you should use the double slash operator / for integer division to ensure correctness. Being mindful of these mistakes will help you build a more robust solution. Another challenge to be aware of is whitespace handling. If the input string contains spaces, failing to account for them can lead to parsing errors. A simple solution is to remove all whitespace from the string before processing or to dynamically skip spaces as you parse. Additionally, mutating the input string while iterating over it can cause problems. For example, directly modifying the string by popping characters may lead to index errors or skipped characters during processing. To prevent this, you can use indices to navigate the string, or convert it into a list for more controlled manipulation. These adjustments ensure that your implementation is both flexible and error-free when handling diverse inputs. This problem is designed to test several key skills, such as parsing, stack usage, and recursion, which are critical for many similar challenges. While a straightforward approach often relies on recursion to evaluate expressions within parentheses, more optimized solutions use a single stack to handle both operators and numbers, reducing memory overhead. It's also important to consider edge cases, such as empty strings, invalid expressions, or deeply nested parentheses, and clearly explain how your code handles them. Interviewers might also ask follow-up questions, like how your solution scales with longer inputs or how to adapt it for floating point numbers or additional operators, such as exponentiation. Understanding these nuances enhances your ability to tackle variations of this problem. Additionally, you'll find this problem closely related to others like LeetCode number 224, which focuses on basic calculations with addition, subtraction, and parentheses, and LeetCode number 227, which introduces multiplication and division but excludes parentheses. Other related problems include LeetCode number 150, which deals with evaluating reverse Polish notation, a parsing problem that focuses on postfix expressions, and LeetCode number 856, which simplifies the task to computing a score based on nested parentheses. When it comes to alternative approaches, one option is recursive descent parsing. This method evaluates expressions recursively as you encounter sub-expressions, such as those within parentheses. While it's straightforward and easy to understand, it can result in stack overflow with deeply nested inputs. Another option is the two-stack method, where one stack handles operators and the other handles operands. This approach is effective for managing precedence but requires additional memory. A more advanced method is single-stack in-place parsing, where a single stack is used to manage both operators and operands, evaluating expressions as you process them. While this approach is more memory efficient, it can be tricky to implement correctly, especially when dealing with parentheses. Each of these techniques offers trade-offs, so choose the one that best suits your needs and constraints. Great job following along. We reviewed the key concepts, including stack-based parsing and operator precedence, that make solving basic calculator 3 efficient and effective. Keep practicing these techniques for similar problems. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!